Number 8. What is the absolute value of 2 and of -2? Explain your response. So this is what they're asking. Y'all probably recognize those symbols. A lot of students, what happened right here, they forget. They get this one right because the absolute value of -2 is 2. Sorry, I'm not on my pen. The absolute value of -2 is 2, but then they miss this one because they mistakenly think that absolute value means write down the opposite. The opposite of -2 is 2, but that's not what absolute value means. Absolute value means when we're taking the absolute value of an integer, what we're asking is how far or what is the distance that number, that integer is to 0. And so if you know your number line and you say, what is the absolute value of 2? I'm asking you, how far away is 2 from 0? Well, it's 2 units away. We're ignoring direction. We don't care if we're going from 2 to 0 or 0 to 2. We're ignoring direction, so signs don't matter. It's 2 units away. This distance from here to here is a distance of 2. And then when we're saying what's the absolute value of -2, we're saying the same thing. How far is it from 0 to -2? That's also a distance of 2. So where a lot of students mess up and have a misconception and think that absolute value means the opposite, it does not. Remember, absolute value is a distance. And how many rulers have you seen that have negative numbers on them? Well, none, because they don't have rulers with negative numbers because distance is not ever negative. You can do this on Desmos. All you have to do, you do have to open up the little thing down here. There might be a way to actually type it in using your keyboard, but this button right here will get your absolute value bar, and then you just type in 2 and it'll tell you 2, or you can back it up and type in -2 and it'll tell you 2. So you can use this side over here just like a regular calculator. Okay, going back to number 9, solve for x. You're going to solve for x by undoing everything that's happened to x in the opposite order. So the first thing that happens to x is that it's being multiplied by 3. The next thing that's happening to the x is we're going to add y to it. And then the third thing that's happening to x is we're going to divide it by z. So we're going to undo each one of those. The opposite of multiply is divide. The opposite of add is subtract. The opposite of divide is multiply. But we're going to go backwards. We're going to work from the bottom up. So the first thing we're going to do on this problem is we're going to multiply. You can use a dot or an X. I probably think a dot would be better because we don't want it to get confused with that X. We're going to multiply both sides by Z. Why? Because that's the last thing that we did was divide by Z. Then the Z's are going to divide out over here, and we're going to be left with 3x plus y equals 2z. Okay, then the next thing we're going to do, we've taken care of that one, so we got to go up to the next step. It says that we add y, so what's the opposite of add y? Subtract y. Subtract y from both sides. So when we subtract y from a positive y, we're left with 0. And bring the 3x down, 3x plus 0 is just 3x. And you can't actually combine those, so we're just going to say 2z minus y. And then, so that means we've taken care of that one, and now we've got to undo multiplying by 3. How do you undo multiplying by 3? You divide by 3. And you have to divide everything by 3. That's going to leave us with x is equal to 2z minus y divided by 3. And that is an answer, and it bothers students because it's not a number. But if we have several variables in here, then we're going to have several variables in the answer. But we have solved it for x. Solve for x means get the x by itself. Number 10, which point is a solution to the equation? The way we're going to do this, to show your work, you would simply take each one of these. Remember, every ordered pair is an x value and a y value. Okay, so if this 1 is the first number, then in its next value, we can replace the x in that equation with that 1, and then we can take the y out and put that in the equation, put the 2 in the equation for the y, and now we've got to see, is this side really equal to 4? If it does equal 4, then it is a solution. If it does not equal 4, then it's not a solution. So 6 times 1 is 6, and 5 times 2 is 10, and 6 minus 10 is negative 4. There was a question mark right there, and now we can say is not equal to 4. So negative 4 is not equal to 4. So we would say this one is not a solution. Now, you can use Desmos to check your work. If I'm asking you to show your work, and I always ask you to show your work, this is what I expect to see. But that does not stop you from going to Desmos and saying, hey, is this going to be true? Well, you can do it 2 ways. You can say, okay, I'm going to type in 6, and I'm going to use the times button down here. 6 times, what am I plugging in? 1. And then I'm going to say minus 5 times, what number did I plug in for y? 2. And it's going to tell me that when I plug in 1 right here and 2 right here, that value is equal to negative 4. And we see that it's supposed to be equal to 4. So we got, they were not equal. We needed to get 4 right here for an answer in order for that to be true. You can check your answer visually by, if you plot the point that we're checking 1, 2, we see that it's not on that line. So the fact that that dot right there is not on that line means that it's not a solution, because the dot has to be on the line to be a solution. So plug in the next point. You would plug in negative 1 right there and negative 2 right there, and negative 1, negative 2, look, it gave you 4. It's supposed to give you 4. It did give you 4. When you check it, what you find out right here is there's that point and it's on the line. So that's a graphical way to show that, yes, it is a solution. Here we're showing it algebraically or numerically. We're doing the calculations and we're coming out with 4, like it said right here that we were supposed to. And here we're showing our work graphically. There's always more than one representation. So go ahead and finish those last 2, C and D, and see if those are solutions or not. You can do it. Be sure you show your work, or you can, put it on the graph. I think on the Desmos activity, I have a way for you to do both. Now, the last one, number 11, wants you to find the domain and range. Remember, domain is the set of x values. Range is the set of y values that are used in the function or the relation. This one's not a function. So this one right here, if you don't have a picture to look at, you have to ask yourself, is there any number for x that I can't plug in? And I would say, no, I can plug in any number that I want to. And some of you may say, well, I can always plug in any number that I want to. No, you can't, not if you're working with real numbers. If this was the square root of x, we can't plug in negative numbers right there, because a negative square root is imaginary. So there would be a restriction. If this was 2 square root of x, y equals 2 square root of x, that you couldn't plug in any number that you want to. You can't plug in negatives. If it was y equals 1 over x, you can't plug in 0. Why? You can't have 0 in the denominator. But for this one right here, if you just want to multiply a number times 2, are there any numbers that you can't multiply by 2? Nope, there are no numbers. You can multiply any number by 2. And you can take any number and add 1 to it. So you can plug in any number that you want, and you're going to get every kind of answer that you can. So there are... the domain and range of both of this is all real numbers. And we're going to learn in just a week or two another way to write this one. I do want to show you graphically, because graphically you might get a better idea. But if we jump over here and look at this graph right here, here's y equals 2x plus 1. We see that if you click on the line, it shows you that point. Okay, so you see the x value of 1.08, 1.27, 1.3, 1.4, 1.9, 1.2. I mean, you see how the values are changing? They're just getting bigger as I roll. Well, as I scroll this and move it, my x values just keep getting bigger And as I go back, my x values just keep getting bigger. So do you see any restrictions, or my x values turning around and they stop getting bigger and they start getting smaller? Nope. As long as I can move this out, they just keep getting bigger and bigger and bigger. And this line's going to go on forever. So that means that my x values are just going to keep getting bigger forever. Well, what about on the other end? What if I'd gone this way? Well, now they're going negative. And they just keep going negative. Negative 15, negative 19, negative 20, negative 30, negative 40. So they're just going to keep getting negative. So that's a good way to show that x values are going to keep going. And now you go back and pay attention to the y values. Look how low the y values are. It's negative 97, negative 105. And if we go up this other way, then we see that they're up high, like 75. The y values are getting bigger and bigger and bigger. So both of these, the domain and the range, the numbers just kept going. This one right here, you see there's 3 numbers in the domain, there's 3 numbers in the range. The domain is always the input. This is the domain right here. And this is the range right here. Okay, so we've got domain is the input, range is the output, always. X is the input, Y is the output. That's how we always do it. So let's look at this one. I put this one on Desmos, and you can click it right here, and you can see, okay, my X values are 0.8, 1.1, 1.2, 2.7, 3.76, 4.45. And then they get out here and it gets to 5. My X value is 5. And then when I go this way, well, now my X values are 4s again, 3s again, 2s again. Now they're negatives. And they go negative 4, negative 4, negative 4, and it goes to... So do you see that the X values don't go on and on and on forever? They're limited. They're only limited. The X values can only be any number that's between what? Negative 5 and positive 5. Algebraic way to write it is to say the X values are between, and that's how we say less than negative 5 and 5. We put the X in the middle. X is between negative 5 and 5. So the X values are going to be bigger than negative 5, but they're going to be smaller than positive 5. And then we do the same thing for the range on this one. The range, it's not unlimited. You can go back and see that if you click on the range, now let's pay attention to the Y values now. This Y value is negative 0.8. Now it's at now it's at 0. Now the Y value is 0.5, 0.7, 0.9, and then it goes up to 1, and now it's going back down. It's 0.9 again, 0.8, 0.7, 0.4, and then down here it's at negative 0.4, negative 0.9, and now it's at negative 1. Now it's going up again. So if you pay attention to the Y values, we're bouncing between Y values. The smallest one is negative 1, and the biggest one is positive 1. So how do we write this? It would be the same way. We would say Y values is what we deal with when we're dealing with range. We'd put them in the middle, and it's going to go between negative 1 and positive 1. Okay, this one, it goes forever up and to the right. That keeps going up and it keeps going to the right. It keeps going down, it keeps going left. So this one has the same behavior as this one. They did the same thing. The only thing different, it has that little curve in the middle. So this is also all real numbers. And again, we'll talk about how to write this in different ways in just a few lessons. It's not very many lessons. I don't know. 2.4, I think. How many lines of symmetry exist in this figure right here? Lines of symmetry, remember, are lines that cut the picture into 2 equal parts. So if you draw a line right here, lines of symmetry, if you draw a line right there, you get the right side and the left side are absolutely identical. Okay, go back and erase that line, and this time let's draw a line right down the middle. Lines of symmetry are always going to be on the middle. Right down the middle that way. And then we have a top half that matches the bottom half exactly. So this one had 2 lines of symmetry.